Ashwin. Please share the link. So, welcome to the fourth day of GIAN program on zeros of L functions. Yesterday we stopped at a theorem where which was necessary for proving the prime number theorem via Newman's method. Okay, and this was okay. Let's do just a recall of what we have done till now about the prime number theorem. And this is pi x is of the order x by log x. Okay. Actually, you may ask them to shift to the YouTube video today, because if I use this, there will be a sound overlap, and so yeah. No, there will be a sound overlap. So that theta x is of the order x, which is equivalent to show that xi x is of the order x as well, and then that is equivalent to show that the integral from 1 to infinity xi x minus x by x square dx converges. Okay. And now, in order to show this, we would prove this theorem that if G S is a function that is analytic in real part of S greater than or equal to 1, such that Gs is equal to this integral from 1 to infinity fx by x to the power 1 plus s dx for real part of S greater than 1 for some function fx which is big O of x, then g of 1 is given by the integral from 1 to infinity fx by x square dx. Okay. In particular, we would put this fx as xi x minus x. Okay. We already know that xi x is big O of x, so xi x minus x satisfies the condition on fx. Okay.
Sir,
yes?
it is both equivalent or one side?
Which one? Ah, right. Yeah, sorry. Thanks a lot. Yeah, we have shown that if this converges, then that will imply that xi x is of the order x. So now we interpret this. We just made some substitutions, like we have put s equal to 1 plus z, x equal to e power t, and just define zz equal to g of s and capital F t as capital F x as fx by x. Then this theorem we restate it as theorem dash say, and that is if gz is a function of z which is analytic in the region real part of z greater than or equal to 0, or a function that is in real part of z greater than or equal to 0, then, well, and also there exists a function capital F okay, I use this part of the word. Okay. This is the function that is analytic in real part of z greater than or equal to 0, then and there exists a bounded function if such that gz is given by the integral, oh no, I think it will be back in a moment. Have you shared the link already, the YouTube link with the GIAN authorities as well, the email? Okay, thank you. Yeah, let's wait for 2 minutes till it comes back. Silence, please. So gz is, well, it should be the integral from, because we are replacing x with e power t. This will be the integral from 0 to infinity f z by e t z dz. Sorry, dt. Excuse me. Okay. For all z with real part of z greater than 0. Okay. Then g of 0 is equal to the integral from 0 to infinity just fz, because t is equal to 0. So this one is just 1. Okay. Fz. Wait a minute. So
it is f e to the power t.
If
Capital F e to the power t.
right, yeah, that was the thing. Yeah. So thanks a lot. Yeah, that was the thing, because it was fx, right? Thanks. Thank you. So f e power t dt. Okay. So we are going to show this, and in order to show this, we defined an auxiliary function, that is gt, which is a truncation of g from the, instead of this integral from 0 to infinity, we are taking the integral from 0 to t. Okay. All right. So integral from, we defined gt z as the integral from 0 to t of the same thing, f of et by e power tz dt. Okay. I note that since this is a bounded function, this function is going to be analytic everywhere. Okay. Now, we have to show, so this one now boils down to show that g0 is the limit of gt0 as t goes to infinity. So suffices to show that g0 is a limit of t going to 0, t going to infinity, excuse me, gt 0. Okay, and we want to show this via contour integration over some nice dome, no, some nice contour. Okay. So this is just limit of t going to infinity g0 minus gt 0 to be equal to 0. That's what we want to show. Okay. So now note that g0 minus gt0, this is, okay, by Cauchy's residual theorem, we get that if we define some, I mean, if the function that we are writing on that right hand side over some contour over on the right hand side, if it has a simple pole at 0 and is analytic on the everywhere on the contour, then we will get here that this is, oh yeah, I mean, so the contour at first we don't know, I mean, before we describe the shape of the contour, all we require is that this should go in some region around this, and where in this region there will be a simple pole only at, and the problem will be only at the origin. Okay, so this one we are integrating over some contour C, and this is gz minus gtz, and we said that we need some kernel function here, that is e power zt 1 plus z square by r square by z. Okay, this is giving rise to the residue. Now what we, okay, now we define the contour precisely, on what contour we are going to do this integration, and then we will handle this part by part on different parts of the contour. Okay. Okay. So this one was a contour that we are considering. Take the unit circle and so two other chalks. Is it visible? Green on green? Okay. And also we saw that since G0, GT is analytic everywhere, right? And G0, I mean GZ is given to be analytic in this region, real part of Z greater than or equal to 0. So every point has some neighborhood in which the function is analytic, right? And since it's a compact region, you can take a finite subcover and take the minimum radius of the open ball around the points. So you can take actually a cover with open balls around each of the point and take the minimum radius of the such balls then in that compact subcover. Okay. So that gives you some radius delta where you can extend this. Okay. So you are extending the circle and you are taking this region, this closed region. So this part is open, the green part is open, and this first part is closed, say. So here we are, I mean, we are extending the, because we will treat this, I mean, treat the integral on this part and treat the integral on this part separately. Okay. Now for this part, the green part, okay, that is where the real part of z is greater than 0. Let's consider this first. Sorry. Yes. Yes. So you can. Have I used capital? Right. Yeah. Sorry. So this is the radius of the circle, and t is just the point of truncation of this. Okay. So there are two things which we are going to vary later in the proof. That is this capital R and t, and this distance is just delta, some delta. Okay. So yeah, or yeah. So you can actually mark this point. Well, call this just minus delta 0. Okay. This point. All right. So now we are going to handle this green part. So real part of no, let's write it down here. That is real part of z greater than 0. Okay. And there what happens, the integral over the green part, over the, I mean, the part of the contour which is here. So we can actually call this part, say, the positive side of the contour. So C plus maybe, and this one the negative side, C minus. Okay. So the integral of the thing on C plus gz minus gtz est 1 plus z square by r square dz by z. We first consider this one. Okay. All right. Now look at this one. Okay, gz minus gtz. What is that? This is the integral from t to infinity, right? T to infinity of f et by e tz dt, right? Now note that f is bounded, right? So suppose it is bounded by some constant. Okay. So suppose f et is bounded by some constant c. Okay, we are using their c and c plus, so maybe we use some other notation here. Maybe bounded by b. Okay. And then this one is bounded by b t to infinity 1 by, sorry, okay, wait a minute. So if we take the I need some more space also to write this one. Can I clear up this part of the board? Thank you. Okay. So this one is bounded by the integral from t to infinity of f et by power tz dt, which is equal to, well, which is also bounded by, because this is bounded by b, so this is bounded by b times, yes, which one, z, z is a complex valued number, yes, of course. In which one? Ah, right, thank you very much. Yes, I am considering the mod. Thanks a lot. Yeah, thank you, Shujit. So this one is bounded by b times t to infinity dt by, well, then what we get in the denominator, it is etz, and that is, we saw this earlier, right? The real part of this. Okay. Yeah. Okay. So this is just b times integral of t to infinity dt by e power real part of ez. And what's that? Can we do this integral? Yes. Minus real part of, okay, wait a minute, minus real part of z times capital T, right, by real part of z, okay, because we are considering z to be on the positive side. Okay. So this part is bounded by such an expression. Okay. Now look at the, well, we have not yet considered what happens after you multiply this, but that would be easy. Okay. So if you take the absolute value of this on this part of the contour, what happens? Okay, consider that e power zt 1 plus z square by r square. So this one is this one on this line, okay, on the green part. This is what happens to e power zt. Yes, but it is e power real part of z times t. Okay, exactly this one, but without this negative sign. Okay, e power real part of z times t. Okay, the first thing. Okay, and now how this times this, you multiply that inside. Okay, you get here z by r. Okay, and here it is just 1 by z, right? So you have here 1 by z plus, no, not z by r, but z by r squared. Okay, well, take one r out. Okay, so which one? Ah, right, sure. Yeah, so thanks a lot. So this is 1 by z plus z by r square, right? Okay, and then if you take one r out, what will happen? E power real part of z times t by r times r by z plus z by r, right? Okay, all right, I'll clear up some part and then we proceed with this. So if your point Z is on the circle of radius r, then can you say what is z bar equal to? It's on the circle of radius r. Root r square, right? It's r square. So that means z bar by r is equal to r by z, right? On the circle. Okay. So you can replace this r by z with z bar by r when you are on this green line. Okay. So this becomes then e power real part of z times t by r, and here you have z bar by r plus z by r. Okay. What is that? Right. So this is 2 into real part of z by r. Well, we can also put, okay, but real part of z is positive, right? So we don't need the absolute value anymore here. Real part of z by r times this thing what was outside. So e power real part of z times t by r, another r. Okay, so it's r squared and e power real part of z times t. Okay, all right. So that is the absolute value from this one. Okay, and when you multiply this and this, what happens? Because we are considering this entire integral on this part, on the part c plus. Okay, so you multiply this, you see that e power minus real part of zt, this gets cancelled with this one. Here there is a real part of z which gets cancelled with this one, and there remains only 2 by r square here and b here. So the product of these two things. Okay, that implies that this integral on the green part is bounded by 2b by r squared. Okay. Exactly. Yeah. Choice of this kernel was such that this cancels. Right. Okay. So on the green part, or on C plus, we have written just. We have that the integral 1 by 2 pi I integral from, well, just this integral, right? We don't have to even consider this one at the moment. So this on C plus g z minus g t z times e z t 1 plus z squared by r squared dz by z. This integral remains bounded by 2b by r squared, right? Yes. Instead of, again, right, integration of dz. Okay, we have just divided this. Okay, let's write it down again. So this part was, this is less than equal to integral of c plus, okay, GTZ times EZT 1 plus Z squared by R squared 1 by Z. Okay, wait a minute. So we handled this this part together. I mean separately this kernel and this one, right? Okay, and then we saw that this integral is bounded and this is bounded by some constant which is cancelling with this part, right? Now, okay, you are saying that what happens, I mean, with dz, but aren't we multiplying it already? I mean, didn't we consider this integral? This integral we have already considered, right? And then we have shown that this remains bounded by this thing. Okay, so wait a minute. Yeah, yeah, tell me again that. Well, we can do that again. Yeah,
Integration C of suppose HZ.
yes,
Do we take the bound of HZ?
yes,
Integration of DZ.
right,
Taking the bound of not HZ.
okay. And so yes, of course, I mean at most there will be an extra r which cancels with this r squared, right? Because this is a bounded region, right? So and the length of this is just pi r, right? So there will be some constant times an extra r. What? Which inequality? You are integrating over a contour, right? And then your z is moving over this contour. So at most it can contribute the length of the contour, right? So Ria was saying that there will be an extra factor of dz, okay, which can at most contribute over this contour of length c plus the length pi r, right? Can it contribute anything more? Because you are taking the absolute value. I mean the length of that contour integration over a path. What does it mean? Okay. Yes. Okay. Just tell them. Yes. Okay. So this one is then bounded by some constant, well, maybe b dash, then by r, right? And then we have this on the left hand side. Okay, this c minus should also be considered, right? And here